The measure of fit for the linear trend line is the topic of this lecture. So we'll define what's called the coefficient of determination, or R squared. Before we can do that, we need to define some other variables called the TSS and the ESS for total sum of squares and explain sum of squares. So we have a standard setup with an OLS trend line calculated from n observations of a y variable and an x variable, and it has an intercept, so it's b1 plus b2x, and it's the OLS trend line, so b1 is calculated from the OLS formula, as is b2. We have from b1 and b2 we have calculated fitted values and residuals. So we have this standard setup where x is number of hours the students have studied and y is the result on the final exam. b1 and b2 calculated using the linest function, which calculates the OLS values for us. And then we have the fitted values and the residuals. So the first one we will define is the TSS, and that's part of a trio which we name TSS, ESS, and RSS. The SS in all cases stands for sum of squares, and some authors prefer to put the SS in front of the T, E, and R. The T is for total, the E is for explained, and R is for residuals. So you can also see SST, SSE, and SSR. So let's move along defining them. The first one, total sum of squares, is defined as follows. It's the sum, and what we're summing is the squared deviation from the mean of the dependent variable, the one that we are explaining. If you look at this formula, it looks very close and very similar to the sample variance of y. The sample variance of y, that's something we denote by s squared y, is defined as 1 over n minus 1, and then this sum, yi minus y bar square, where this sum here, that's the thing we call total sum of squares. So if I multiply both sides by n minus 1, we can also see that TSS is the same thing as n minus 1 times the sample variance of y. So let's use this result to easily compute TSS for my particular data. So I can calculate TSS as n minus 1 times the sample variance. In my case, n is 9 observations, so it's 8 times VAR dot S for sample variance of the y data. That's my TSS. This is the total sum of squares. Next we have ESS, which is explained sum of squares. And this is a similar concept but using fitted values instead of the actual values. So again, if we look at the sample variance of the fitted values, the sample variance of the fitted values, that's denoted like this. Then it's defined as 1 over n minus 1 summation. Then I should put the fitted values here, and I should put the average or sample mean of the fitted values. Close it and square it. That's the definition. But we already know from a previous result that the average of the fitted values is precisely the same as the average of the y data. So I can just replace this with y bar. And this part here is then my ESS. So again, multiplying by n minus 1, ESS is n minus 1 sy hat square. So let's do the ESS. N minus 1, 8 times VAR dot S of fitted values. Like that, 1686.7. And the final SS concept, sum of square concept, is the RSS, residual sum of squares. And we've seen that before. It's just the sum of the squares of the residuals. So we can fill that out also. So we have the complete trio. It is sum SQ. Well, let's use the same formula, because we can use exactly the same formula. 8 times the sample variance of the residuals. VAR.S. This will be exactly the same as the sum of squares of the residuals. And the reason for that is, of course, that the sample variance of the residuals, by definition, 1n minus 1, summation EI minus E bar square. Well, we know that this is 0, so this is 1n minus 1, summation EI square. This is RSS. So we can also write it like this. RSS is n minus 1 times the sample variance in the residuals. The notation for this trio of squared residuals is unfortunately quite confusing because there exists so many variations. I discussed previously that some authors put the SS in front of TE and R, but it's actually even worse because some authors will call this expression here the expression that we have denoted by RSS, they will call that ESS. And this expression that we have called ESS, they will call RSS. And their motivation then is that the RSS stands for regression sum of squares and the ESS stands for error sum of squares. So lots of confusion about the notation. Whenever you look at sum of squares, you have to be careful at looking at what exactly is the definition that the particular author is using. So we also have these three connections between the SS and the sample variance. The sample variance in the Y data is TSS over n minus 1, or alternatively, TSS is n minus 1 times the sample variance in the Y data. The sample variance in the fitted data is ESS over n minus 1, and the sample variance in the residual data is RSS over n minus 1. With these definitions, we are ready to define the coefficient of determination, or R square. First, an important result, and it's as follows. If you sum ESS, explained sum of squares, and RSS, residual sum of squares, you will get TSS, total sum of squares. Let's check that we also get that. So let's do ESS plus RSS. Let's sum these two. And we see that we get exactly the same as TSS. This cell here is the same as that. And again, we will always get that result as long as we use the OLS values for B1 and B2, no matter what the data is. So change your data completely or partly. So if I change this to, I don't know, something 145, pretty much everything in the sheet will change. B1 and B2 will change, fitted values will change, residuals will change, TSS will not change, but ESS and RSS will change, but they will still sum up to TSS. So in this case, we got this, and you can see that it's still true that they sum to TSS. We are not going to prove this result in this lecture, but just state it as a fact that TSS is ESS plus RSS. And we are going to give some interpretations of these sum of squares. So the TSS, that is viewed as the total variation in the data and in the Y data in this case, the variable that we're trying to explain. So we think of the TSS as the total variation in the dependent variable or the Y variable. The explained sum of square ESS, we think about that as the part of the variation in the Y data that we can explain with our linear trend line. ESS is the part of the total variation that we can explain. And we think of RSS as the part of the total variation that we cannot explain. So summing these two up, the part that we can explain with the linear trend line and the part that we cannot explain with the linear trend line, gives you the total variation. This is the basis of our definition of R square, or coefficient of determination. So we define R square as ESS over TSS. If you think about ESS as the part you can explain and TSS as the total variation, then R square is simply the proportion of the total variation that you can explain with the linear trend line. Since ESS is TSS minus RSS, we can also write that as 1 minus RSS over TSS. And since RSS is the part of the or is the total variation that you cannot explain, this ratio RSS over TSS is the proportion that you cannot explain. So 1 minus that proportion is the proportion that you can explain. So a high R square is good news. That means that we have been able to explain a high proportion of the total variation with our trend line. A small R square is bad news. That means that the trend line does not fit the data very well at all. Now it's very easy to see that R square, being a proportion, must be between 0 and 1. The lowest value it can take is 0. That means that we explain 0% of the total variation with our linear trend line. And it can be 1, which means that we explain 100%. To see that R square must be between 0 and 1, just remember we have this relationship. Both of these, or sorry, all three of these S's are sum of squares. So all of them must be greater than or equal to 0 because we all sum non-negative numbers. So this is greater than or equal to 0, this 2, and this 2. That means that ESS and RSS must each be less than TSS, less than or equal to. So ESS must be somewhere between 0 and at most equal to TSS. ESS can never be greater than TSS because that would imply a negative RSS, which is not possible. And the same thing goes for RSS. It must be between 0 and TSS. So if you now then look at R square as ESS over TSS, you can see that R square must be greater than or equal to 0 simply because I'm dividing two numbers which cannot be negative. And you can see that R square must be less than or equal to 1 simply because ESS, the number here, can never be greater than the number here. It's less than or equal to TSS. So R square must be between 0 and 1. In our case, we have a coefficient of determination, which is ESS divided by TSS. So it's about 91%. And the way we interpret that is that 91% of the variation in Y is explained by the linear trend line, 9% is unexplained due to the residuals. So let's have a look at the extreme cases of R square being 1 and R square being 0. So I have a simple example here with just some made up data of 10 observations. X goes from 1 to 10, and Y is just twice as big as X for all observations. So Y goes from 2 to 20. So you can see that in the scatter plot here, all the blue points line up perfectly on a straight line, since the Y value is exactly twice the X value. The least squares fitted line will pick up this, of course, and find the trend line to have a slope of 2 and an intercept of 0. And the case here is that now all the data is exactly on the trend line. So that also means that all the fitted values are equal to the actual values. The fitted values are calculated as B1 plus 2 times xi, so the fitted values will be exactly the same as the y values. And the difference between y and fitted values, the residuals, will all be 0. In this particular case, if you calculate TS, I just noticed I haven't changed this one. It's n minus 1, so it's now 9. So now I've updated it with the correct value for n. So in this case, the TSS, total sum of squares, the total variation in the y data is 320. ESS is the total variation in the fitted values. Well, since the fitted values are exactly the same as the y data, the fitted values have the same variation. So ESS is 330 as well. So what we say in this case is that the linear trend line explains all of the variation in the y data, leaving nothing for the residuals. There are no residuals, so RSS is 0, and that means that R square is 1. We explain 100% of the data. This will always happen when all your observations line up on a perfectly straight line. So let's try and go to the opposite case. If I take this y value down to 0, I'm going to move this point down to 0. That, of course, is going to ruin my perfect fit. And we can see that it's going to take R squared down to 99%. By the way, I should remove these now because they don't update when you change the data. You have to add them and remove them again. So now I'm able to explain 99% of the data. So let's keep on changing a couple of these. So let's do 0, 0, 0. Let's keep this at 10. Move this as well to 10. So we have 2 at 10, and then take these down to 0. And you can see now that I've gone all the way down to an R square of 0. If you look at the data now, if you try to fit a straight line through this data, you get this dashed line here. What happens in this case is that all the fitted values are the same, constant equal to 2, because the trend line is a straight line. That means that there is no variation at all in the fitted values. So the TSS, which is now 160, the ESS is 0. That means that we can explain nothing with our linear trend line. If you look at RSS, you can see that I made some mistake here because RSS can never be greater than TSS, let's look at that. It's D4 to D12. Those are not the correct references. It should be D2 to D11. So now RSS is the value that we would expect, 160. So it's still true that ESS plus RSS is the same as TSS, but in this case, ESS is 0, we explain nothing. The entire variation in the Y data is due to the residuals. So R squared for this particular case becomes 0.